In mathematics, calculating the output of a function is usually straightforward, but working backward, identifying the exact inputs that produced a specific output, is a much harder problem. Today, we're looking at how to mathematically reverse a complex multivariable function. We can see the baseline for this in one dimension. Take this parabola, y equals x squared. Zooming in where the slope is non-zero, the curve passes the horizontal line test. Every y value traces to exactly one x value, making it reversible. But when the derivative equals 0, the curve flattens. A single horizontal line hits multiple points, making it impossible to reverse. When moving from a single variable to multidimensional spaces, mapping from Rn to Rn, a single slope isn't enough. We use the Jacobian matrix. This collects all the first-order partial derivatives of a system into a single grid. To determine if we can reverse a function, this matrix must be non-singular, meaning its determinant is not 0. Evaluating this matrix reveals whether the forward progress of a highly complex system can be untangled and mapped backward. To understand what that matrix represents, look at how multivariable functions behave. They warp, stretch, and bend the coordinate space. If you look closely enough at any specific point, that curved distortion straightens out. At a microscopic level, the transformation resembles a flat, uniform linear change. The Jacobian matrix is the mathematical representation of that local linear flatness. The determinant is the indicator of reversibility. If the Jacobian's determinant equals 0, the transformation squashes the space, like flattening a 2D sheet of paper into a 1D line. This destroys spatial information, making it impossible to reconstruct the original shape. Walter Rudin formalized the navigation of these spaces in Chapter 9 of Principles of Mathematical Analysis. In practical terms, the inverse function theorem states that if a function is continuously differentiable and its Jacobian determinant is non-zero, a local one-to-one mapping is guaranteed. The theorem also provides the formula for this new inverse function. The derivative of the inverse at target point y is the matrix inverse of our original Jacobian, evaluated at x. This theorem proves a local reverse function exists and provides the algebraic blueprint to compute its rate of change. Let's test this with a practical computation. This is the standard polar coordinate transformation, mapping radius and angle into x and y coordinates. Pause the video here. Construct the 2x2 Jacobian matrix for this equation and compute its determinant. Taking the partial derivatives of x and y with respect to r and theta reveals the matrix. Multiplying the diagonals and subtracting shows that the final determinant simplifies to exactly r. Because the determinant equals the radius, it is non-zero everywhere except at the exact origin. The theorem guarantees invertibility for any non-zero radius. There is a critical distinction between local and global invertibility. Even with a non-zero determinant at a radius of 1, an input angle of 0 and an input angle of 2 pi map to the same physical location. The inverse function theorem is strictly a local tool. It guarantees you can reverse your steps safely within a tiny neighborhood, but it makes no promises about the global behavior of the function crossing over itself elsewhere. Navigating these localized, multidimensional spaces is a requirement in many applied sciences. Fields like robotics or machine learning rely on inverse kinematics. Engineers use this theorem to prove whether a robotic arm's target physical position or a specific data state in a network can be traced back to its starting parameters. Here are the 3 core rules. 1. A non-zero Jacobian determinant guarantees a local inverse. 2. This concept scales one-dimensional derivative rules into multidimensional matrices. 3. The derivative of the inverse is the matrix inverse of the original derivative. The inverse function theorem serves as the definitive bridge connecting the geometry of linear algebra with the rates of change in calculus. Proving that local linear behavior dictates multivariable reversals allows us to navigate complex systems backward. If you found this breakdown helpful, subscribe and follow along for the next chapter analysis.